Alright, we're looking at our tangent segments. Our first problem here, well, first of all, tangent segments are part of a tangent line, a segment, with one endpoint outside the circle and one at the point of tangent to the circle. So BD and CD are tangent segments. That's what this says. But the tangent segments to the circle from a point outside the circle are congruent. So we have these tangent segments, BD and DC, and we want to prove them. BD is congruent to DC. That's our proof here. I'm going to do two-column proof. You could do a flow chart or paragraph proof if you'd like. It doesn't matter. So first thing we're going to start with is, like always, BD and DC are tangent. Given. Then what we want to do is we need to draw some other segments. We don't have anything else here. So draw AB. And we can just draw any lines we want. That's always a thing that we could do. What I'm going to put for a reason is that 2 points determine it may be different in the rest of the book, but that's what we'll do. And then AB is congruent to, because all radii of the circle are congruent. There's no all radii of a circle are congruent. Those are congruent. We also know that B is equal to BD and AC perpendicular to BD. Because radii are perpendicular to the point of tangency of a tangent segment. I mean, it's just showing that you just have to make sense of it. Is it the exact definition we talked about in class? Maybe, maybe not. Doesn't matter. So that means ABC and BC are angles. That's the definition of perpendicular segment. They're perpendicular to right angles. That's the idea. We're going to draw the same reason 2 points in the segment. So now what we have here is we're starting to get 2 triangles, and that's our goal. So AB the reflection property. And triangle BCD and triangle, I can't see the others, ABD are triangles. Never right triangles. Because they have right angles. So what we have is, we have the hypotenuse of each right triangle congruent, we have 2 right triangles, and we have a leg congruent. That is the definition of hypotenuse leg. So, triangle ABD is congruent to ACD. Right? Postulate. We didn't use that a whole lot, but it is something important to see. But that's the thing that we want to prove, that DB is congruent to DC. And why? We'll add the triangle congruent, so all the other segments are congruent as well. So in number 2, I guess we're assuming that all these lines are tangent at A, H, and D. It doesn't say that, but we're going to assume that's true, and I guess we can see that it does intersect just the once at those points. So, TH is congruent to TA by that theorem we just proved. TM is congruent to AM. RD is congruent to RH. So we have all those things congruent. Now what we're going to do is just plug in our segment. Well, RT, this whole thing, is 12. And RH is 5. If RH is 5, RT is 5. And if all of TR is 12 and RH is 5, we subtract with TH. And TH is the same thing. We also know that NT is 21, using our subtraction property again. We know that AM is 14, and we're trying to find RM. RM equals 19. Now what you still have to do is write out in words how we did that. Explain what we just went through. Now if we're looking at letter B, if OH equals 4, and we're trying to find OT, we draw those. So I'm going to draw it a little bit bigger. E, O, and H. Because TH is a tangent segment, we know this is a right angle. We know OH is 4, they tell us. TH is 7, because we already knew that. Now how do we find OT? Simple. We have a right triangle, we use Pythagorean theorem. 4 squared plus 7 squared equals x squared. Solve for x. X is square root of 65. Or a little over 8. So it's just Pythagorean theorem and using our tangent segment theorem. Our homework is going to be these 4 problems. Here are the answers. I want to see work for these, but it's all the same ideas that we just talked about.